So we just learned in our last video about Einstein's revolutionary paper that gave birth to the field of quantum physics. What he saw was he created a device called a photocell where as long as light had a certain frequency or higher, it had enough energy to release an electron. And that amount of energy was found as hf. H is Planck's constant, and f is the frequency of the light wave. And as long as that frequency was high enough, we could release electrons in this photocell. So in this figure, I didn't really describe this figure. Let me do so now. If you have a frequency that's smaller than this base frequency, nothing's going to happen. But once your frequency does hit this frequency, you release an electron. And the higher the frequency, the more electrons we can release. So that tells us that the amount of energy released in this photocell was dependent not on the intensity of light, but on the frequency of light. Therefore, that tells us that all light has some frequency hf, and the total energy is going to be some whole number multiple of this, and this proved Max Planck right. As soon as Einstein came out with this paper, the world of physics went crazy. It was exciting because we all of a sudden see a new world where energy is quantized, and this became a very active field of study and has been in the 115 years since. So now in this video, we're going to actually look a little bit more at these photons. What's some of the behaviors of these photons? Okay, first of all, photons must travel at the speed of light. Okay, that in itself is an interesting question because you start having relativistic stuff. We're not getting into that right now, but we'll just hold on to that for a bit. To find our relativistic equation for momentum, relativistic momentum is energy divided by the speed of light. But energy we know is hf from Max Planck, and if you use the wave equation, c is equal to lambda f, well, that means that f is equal to, sorry, let me rephrase this again. F over c then has to equal 1 over lambda. Plugging that in here, you find that the momentum of a light wave is Max Planck's constant divided by the wavelength of the light. Now this is really interesting because momentum, you have to have mass, right? Remember, we're dealing with relativistic effects here, and so things get a little weird. But point is, photons are a massless particle. They have no mass, but they do have energy. And so they still have momentum, and light has momentum. There are a number of experiments and demonstrations that actually show that light has momentum. It's pretty cool. You can look up the theory of a solar sail. The idea of a solar sail is you spread it out and it catches the photons of the sun and transfers that momentum of light to the momentum of your craft. Kind of a cool idea. All right, so let's talk about some of the behaviors of light now. We saw the photoelectric effect, where once you have a certain amount of energy, an electron can be released. Let's talk about the Compton effect. This is another interesting one, where a photon comes in, hits an electron. That electron can then escape, very much like the photoelectric effect. Bam, electron's gone. But this particular photon happens to have more energy than that, and so the photon is then scattered, turns at a different angle, and it now has a new wavelength. So we have a new wavelength, thus a new frequency. So it might be like violet light hits an electron, the electron goes shooting off like in the photoelectric effect, but you get this red light that comes out of it because the light has changed its frequency due to the loss of energy. You don't need to focus too much on this equation. This equation is just showing that there is a change in wavelength when this photon hits an electron. So this is just the equation from the momentum of a photon. But rearrange, you can find the wavelength of any particle of matter. So if you're traveling along at, say, 10 meters per second, we can find a wavelength of any body of matter this way. And this is interesting. This is quite odd, because now all of a sudden this is showing that every object, including you and me, we behave like waves. We're particles. We are made of actual matter, stuff, and yet we behave like waves. And a lot of experiments have shown that sure enough we do have some sort of a wave-like behavior to us. Okay. In our case, since our mass is so high, our wavelength is extremely low. So for us, our wavelengths are extraordinarily small, but it's still there. When you get to smaller objects such as photons, this does become important, and this is one of the effects. The Compton effect is one of those where you have momentum, but that momentum changes because its wavelength changes as well. Now, electron wavelength, these electrons have waves. Electrons are seriously just little particles that are buzzing around the nucleus of an atom. But they behave like waves, and we can see their wavelengths on the order of 10 to the negative 10th meters. That's a tenth of a nanometer. And yet we can see that. Here's a picture where we can see some of the wavelength idea. You can kind of see, it's not very clear in this picture, but it's there. You can see that it's not a smooth, even circle all the way around, as if my circle that I just drew is smooth and even. It's not smooth and even. It's very rugged and ununiform. And there's another reason to that too, which I'll get at in the last video of this segment. But we can actually see the diffracted electrons using crystals in an and so we can actually see this wave-like motion of an electron. And basically this kind of introduces the idea that you have a nucleus of an atom and an electron has some sort of an orbit, an oscillation, a wave-like pattern around the nucleus. And that's what we're getting at here. Alright, and that'll come up again in the next couple of videos, so hang on to that one for a little bit as well. Here's another weird behavior of photons. Photons have something called pair production. This is a really weird thing. It's happened. We've actually physically observed this. Get ready, because this is weird. A photon, which is massless, and the velocity is around the speed of light, will just sometimes sporadically decompose. The photon will decompose and turn into an electron and something we call a positron, which is an electron but with a positive charge. Basically a positive version of an electron. These things don't last long. If you get a positron in nature, it's going to soon encounter an electron, and when they do, they're going to annihilate each other and turn back into a photon. Now here's the weird thing. Remember, a photon is massless, but both the electron and the positron, both of them have mass. Whoops, sorry, I'm thinking ahead. And the velocity is less than the speed of light. That's kind of, let me see if I can write that more clearly. There we go. The velocity is less than the speed of light. And so this massless photon just randomly decays and turns into electrons and positrons. The positrons then encounter another electron later on down the road, hit each other, and bam, they annihilate each other and turn into a photon. This is called pair production. Just one of those weird behaviors of photons. All right, so here's a good summary of pair production. Sorry, not pair production. A good summary of the behavior of photons. The first is the photoelectric effect. This is what Einstein used to show that Max Planck was right. The second, so basically, let me draw this again. You have a negative plate, you have a positive point. A photon hits, and if it has enough energy, then an electron is going to escape and run across to that positive point on the other side. That's the photoelectric effect. Photons can also be totally absorbed by the electron, but not enough energy to eject it. And so the electron then moves to what we call an excited state. We'll talk about this more with Bohr's model of the atom in our final video. Whoops, sorry, I didn't mean to do an E, I meant to do an atom. There's a nucleus. And these are what we call electron orbitals. So you have an electron here, a photon comes in, hits that electron, the electron gets some energy and starts to escape, but can't quite escape all the way out of the atom, so it just moves up to a higher energy level. That's what we call an excited state. Again, we'll talk about that more when we talk about the Bohr model of the atom. All right, a photon can scatter from an atom and lose some energy. This is the Compton effect, which we talked about a few slides ago. And then you have the pair production, the electron-positron pair. The photon decomposes into positrons and electrons, or the other way around, electrons and positrons hit each other, annihilate each other, and turn back into a photon. Anyway, that's some of the weird and yet cool behavior of a photon, which honestly a lot of this stuff is still being researched today, and there's still some cool stuff that we're learning from this.